Hello, everyone, and welcome to the online causal inference seminar. Today, we're very happy to have Kosuke Imai here today with us, who will be talking about safe policy learning through extrapolation, application to pre-trial risk assessment. In the Q&A, we have Eli Ben Michael from Harvard University. So after Kosuke's talk, we also have Yifan Chui from the National University of Singapore. I'm switching over to Emma now, who will be dealing with the Q&A here today.
All right. Hi, everyone. So as usual, we will be handling questions through the Q&A. So please use the Q&A section at the bottom of your screen to ask questions and not the chat. This kind of allows everyone else to see your question after it's been answered. If you just put it to the chat, people will not be able to see what you've asked, really. Okay. At a few points during the talk, Kosuke will stop and answer questions that I will read out to him. But throughout the talk, Eli has kindly agreed to answer your questions. So please feel free to submit your questions as soon as they come up. All right, that's kind of all I have to say. So we'll let Kosuke take over.
Okay. All right, let me share the slides. Okay, you guys can see this?
Yeah.
Okay, awesome. Yeah, thanks for Georgia for introduction, and thanks the organizers for inviting me. I think it's online causal inference seminar is a great public goods in the era of pandemic. I'm not sure you guys keep going, even maybe post-pandemic, but I really appreciate the opportunity to present this work. So today I want to talk about the paper that's actually on the archive. You can take a look at it. Safe policy learning through extrapolation, application to pretrial risk assessment. And I'm Kosuke Imai. I'm a faculty member in both Department of Government and Statistics Department at Harvard. This is a truly collaborative work, so I want to acknowledge my co-authors. Most importantly, Eli Ben Michael, who's actually here answering questions in Q&A chat. And if I get stuck, he can help me out. Jim Greiner is a faculty member at Harvard Law School, so he knows a lot about pretrial risk assessment scores, and we've been working together for a few years now. And Jichao Jian, who is an assistant professor at the University of Massachusetts Amherst, and he's been also been a long collaborator of mine. So, okay, just to get the motivation for this paper as well as for the project, there is a widespread use of algorithmic recommendations and decisions in today's world. I don't have to give you examples. But on one hand, in the academic literature, we also see the fast-growing literature on policy learning. So a lot of people working on this area. We see lots of interesting intersection with statistics and machine learning. What I want to focus today is high-stake algorithmic recommendations and decisions in perhaps medicine, and most importantly for me, public policy. So these are the use of algorithmic recommendations and decisions, but like really high stake, right? Not like online shopping. I mean, it's important for every one of us, but it may not be that important for the society. And there are a couple of important aspects of this. One is the need for transparency and accountability. So, if you're doing public policy using algorithms, you have to be transparent, and so that somebody can be held accountable for it. For this reason, often the rules that they're using are very simple and deterministic rules. So it's easy to understand for the policymakers as well as for the public. Now, the question that we want to answer is, how can we learn new and better policies using the data based on existing deterministic policies? So oftentimes, in the application that I'm going to introduce you, there is existing deterministic policies out there. And we want to see if we can improve it and come up with better policies. So unfortunately, if you look at most of the policy learning methods out there, they tend to require existing policies to be stochastic. So there's some probability of receiving a particular policy decision regardless of what your profiles might be. So it's not a simple deterministic rules. It's often some experiment or observational studies where you assume there is propensity score bounded between 0 and 1. So what we want to do instead is to develop a safe approach. By safe, what I mean is that try to limit the possibility that we make things worse, right? So that would be the worst thing the statistician can do, is to come with fancy methods and make things worse, right? So we want to be safe in the sense that we want to improve on existing policy, but we don't want to do it worse, make it worse. Okay? And we have to do it through extrapolation because these are deterministic policies, not the stochastic policies. So we have to be very careful when we extrapolate, as we all know. All right, so just to give, that's sort of the motivation of the paper and the project. And to give you the overview of the talk, there's sort of methodological aspects where we're going to find an improved policy over the status quo policy. So that's really important. So the status quo policy is already there, and we want to improve it. We're going to do this by maximizing the expected utility in the worst case scenarios. So there is a set of models that we're going to consider, and we're going to consider the worst case scenario and then try to choose a policy that maximizes the expected utility in this setting. So it's maximum principle. Basically, this fits in a robust optimization approach based on some type of partial identification. Our proposed methodology has statistical safety guarantee. By that, I mean limiting the probability for yielding the worst outcome than the existing policy. So try not to do worse. It's a conservative approach. The application, which I think is of interest in itself, is that pretrial risk assessment instruments used in the US criminal justice system. We have this, our own unique experimental variation in Dane County, Wisconsin. And we're going to try to learn new algorithmic scoring and recommendation rules while maintaining the transparency and the structure of the existing rules that's actually already in place. So this is a field experiment that we've been conducting over the last few years. There's another sort of companion paper that's coming out in the journals. It's AO's discussions that has a lot more details of this experiment and related analysis. So if you're interested, you can take a look. All right, so before I start talking about the methodology, let me give sort of background on the pretrial public safety assessment, because I think this application, is of interest in itself, but also it shows like how typically like public policies uses algorithmic inputs and implement them in the real world. So it turns out the algorithmic recommendations have been used in the US criminal justice for a relatively long time. So it's nothing really new. People have been using data and scoring RSDs and trying to make sure that the judges can make a better decisions. Okay. So the one thing that the particular example of this that we're going to focus on is the case where we at the first appearance hearing. So you do something bad and possibly wrong on the street, and you get arrested. Okay, so you have this first appearance hearing. Judges have to make two decisions: whether to release an arrestee pending disposition of criminal charges. So these people are not yet charged, right? So they could be innocent, but the judge has to decide whether to release you or detain you. Okay. And if they're going to release you, what conditions? With a bail amount or monitoring conditions. The goal for the judge is to avoid the predispositional incarceration while preserving the public safety. So judges are required to consider 3 risk factors along with others. Okay. If the arrestee gets released, they may fail to show up in the court. So they may not come back to the court, which would be a problem. I'm going to call this FDA, fail to appear. Arrestee may engage in new criminal activity while being on release. I'm going to call this new NCA, new criminal activity. And arrestee may engage in new violent criminal activity, which is NVCA. That's the acronym I'm going to use. Okay, so I'm going to use this acronym throughout the talk. PSA, the public safety assessment, is an algorithmic recommendation to judges. It classifies arrestees according to these risks. It's derived from an application of a machine learning algorithm, whatever that is, to a training data set based on past observations. So some kind of statistical model is used. It's proprietary information, so you don't know what it is. It's different from the famous or infamous COMPASS score. So it's a different but similar idea. Now we are fortunate to do a field experiment to evaluate this PSA. And the setting is Dane County, Wisconsin. In this setting, PSA is a weighted indices of 10 different factors. So importantly, age is the only demographic factor. So no gender or race is used in this algorithm. Okay. And then there's 9 different factors drawn from criminal history, prior convictions, prior failure to appear. PSA scores and recommendation consist of 2 separate ordinal 6 risk scores for FTA and NCA. So there's 6-point scores for FTA and NCA separately. And then there's 1 binary flag for new violent criminal activity. And then they also have aggregate recommendation. So here I'm going to focus on signature bond versus cash bond. But the recommendation distinguishes the amount of cash, small or large. Judges may have other information about an arrestee when they're making a decision, along with this PSA score. Okay? So there may be affidavit by a police officer about the arrest, or there may be a defense attorney is present. The field experiment we were able to do was done following fashion. So the clerk assigned case numbers sequentially as cases enter the system. Somebody gets arrested and you enter the system. And then PSA gets calculated for each case using the computer system. And then they basically assign if the first digit of case number is even, PSA is given to the judge. And if it's odd, PSA is not given. So the manipulation here is the provision of PSA, whether the PSA, this information is given or not. And we have sort of this analysis I'm going to show you is based on sort of preliminary data. We have more data coming. So here is the actual report the judge sees. So you can see the judge sees, arrest date, and judge sees the this NVCA flag. This is a binary risk score, and then there are 2 ordinal 6 level scores for new criminal activity and the failure to appear. Okay, and then there's actual charge, and there are risk factors. So risk factors are actually all listed. So it's not that judges getting additional information. It's basically that judges are getting how the sort of summary of this information represented in these 3 different scores. So this is aggregated indifferently. Okay. And then at the end, they have overall recommendation, in this case, signature bond. So signature bond means basically you can sign the piece of paper and then go. All right, so how does the scoring rule works? Okay, so and the important thing is actually that this information is like publicly available. So this is a transparency thing I'm talking about. It's relatively simple, relatively simple. And you can see, like anyone can see this, exactly. And judge also can see this. Okay? So these are the risk factors, and these are the 3 different scores, and these are the point systems. So each element each factor has a point, depending on the risk factor you're trying to calculate. And you basically add these numbers up. Okay? And once you add these numbers up, then you put in the bins. And that becomes 0 to 6 scores. That's sort of 6-point ordinal scores for FTA and NCA, and then binary scale for NVCA. So exact sort of binning is shown here, but basically it's integer weighted, and then total number. There's a threshold based on the total number, and then put in the bins, and becomes the ordinal score. In this paper, we're going to focus on NVCA. So it's a binary score. If it's below 3 or below, it becomes 0. 4 or higher becomes 1. Okay, so we're going to sort of focus on that violent criminal activity score. All right. Once these 3 numbers are calculated, then there's something called the decision-making framework, which gives overall recommendation. Okay, so overall recommendation, if you have NVCA flag 1, you're automatically told to give recommendation is cash bail, which is you have to pay some amount of money to be released, which is the harshest decision in the data we have, because most of the crimes that we have is it's very petty crime, relatively minor crimes. And so the decision-making framework, or DMF, combines NCA score and FDA score and produces the overall recommendation. And as you can see, each one is a 6-point scale, 0 to 6. And then basically, if either of them is higher, 5 or higher, 5 or 6, then this decision-making framework says judge should give a cash bail instead of signature bond. So that's basically the threshold line. The white places are just like theoretically impossible. The way that the integer weights are constructed, there's no observations. You cannot have any observation in these white areas. Right. If you look at the data, what you see that most of the cases are given signature bond instead of cash bail, so people can just leave. Interestingly, like 30% of people don't show up. So FDA rate is like 1/3. How serious that is, it depends on what the crime they committed. And then the outcome we're going to focus on is also binary outcome, whether there is an NVCA or no NVCA when they are released. Okay, and as you can see, unfortunately, there are only 109 observations, which results in new violent criminal activity, and most of the cases are no new violent criminal activity. So that's sort of the background of the application. And maybe I'll stop here just briefly to see if there's any question.
We don't actually have questions at the moment, but
All right,
again,
all right.
oh wait, sorry, we just got one.
Okay.
So I guess I can read it out to you. Are these release decisions being treated as deterministic in both the aggregate, i.e. in the confusion table, and for each individual?
Right, so the decision is not deterministic. So judge still has a say, like in the US. It's not like algorithmic judge will sentence you. Not yet, at least. Right? So the decision has a human element to it, but the algorithm recommendation is deterministic.
Okay, great. Thanks for the clarification.
And that's a really important point. And when I discuss the methodology from now, I'm going to focus on the cases. I'm going to skip the human decision. Okay, in the paper, we sort of talk about that, incorporating the human decision aspect. But for the sake of time, I'm going to sort of focus on a case where we're going to look at the deterministic recommendation and downstream outcome. Okay, so and then in that downstream outcome, in between the human decision of the judge, but also human decision by the arrestee in terms of their behavior is part of that. Okay, so just to set up notation, so for each individual, we observe some covariates. So those are a list of factors we had, and there's some action taken. In this case, it's just algorithmic recommendation. We're going to focus on the case of binary outcome because that's sort of our outcome, but you can extend this framework to non-binary outcome framework. We have potential outcome under action A. Conditional expectation of potential outcome is denoted by M. We have deterministic baseline policy, so that's the policy that I just described, pi tilde. And we observe outcomes under that policy. Okay? So we are observing the outcome under the existing policy that is deterministic. Basically, this ends up just partitioning the covariate space into different action values. And we're going to look at the utility function that has the cost associated with each different actions. And then utility, because it's binary outcome we're looking at, is multiplied by the potential outcome. So the goal here is to find a policy with high expected utility or value or welfare, depending on the field you're in. And so you can think of this value as a expected value of all the possible actions that policy could take, and multiplied by the cost and the utility given the expected potential conditional expectation of potential outcome. An important thing is that this we're going to be looking at a deterministic policy where given x, there's deterministic function pi that gives you what actions should be taken. But as we all know, we can identify this conditional expectation of potential outcome only when the existing policy agrees with that particular value A, right? So in the data set, because data set is generated on the existing policy, if the potential outcome you're interested in is different from the existing policy, then you don't get to observe that. So the question is, how are you going to incorporate that, how to impute this conditional expectation? Okay. Existing work uses stochastic policies to identify these. So there might be an experiment of the algorithmic recommendations or observational studies, right? So you might use the inverse probability weighting or some outcome model imputation or doubly robust methods. Okay. However, the problem here is that we have a deterministic policy, right? So we cannot, given X, the deterministic policy has a probability 1 assigning to a particular action. So we cannot use the inverse probability weighting type of methodology. So we have to do something more, so it's more related to the outcome model imputation with extrapolation. So to do this, we're going to decompose the value into, there's a cost is identified. And the part that the policy that you're looking at agree with the existing policy, in which case we can just simply use this outcome value that we observe, right? Because that's the realized outcome that we can find in the data set. And the part that the policy that you're looking at disagree with the existing policy, in which case we have to sort of figure out what to do with this M function. So there are parts that are identifiable and there are parts that are not identifiable. Okay. And the strategy that we're going to propose is to partially identify this M function in some selected model class, and then find the best policy in the worst case among that model class. Okay. So that's basically the max-min strategy that I mentioned earlier at the beginning of the talk. And it's essentially equivalent to minimizing the regret, right? Maximal regret relative to the baseline policy. Okay. So that's sort of the framework we're gonna use. Okay. And I'm gonna call this a safe policy based on the use of robust optimization. It's safe because it's tried to improve upon the existing policy. Okay. In some sense, it's conservative because we use this max-min principle. And then we're going to fall back on the status quo policy if there is too much uncertainty. So if there is too much uncertainty and say, we can't really be sure that this new policy is going to improve upon existing policy, then we just fall back on the existing policy and then we'll just stick with what we have now. Okay. So how does the partial identification is done? To partially identify conditional expectation, we put some restrictions on the class of possible models. I mean, of course, you don't have to put the restrictions and just try to get bounds, but often some restrictions necessary to make some progress. Then we compute the set of functions in this selected model class, making sure that they agree with the observed data, right? Because there's the data that we observe under the existing policy, and we want to make sure that the model that we are considering actually are consistent with the observed data. Okay. So in many model classes, and in our application in particular, because our application, the covariate is all discrete, it results in a pointwise bounds. In the paper, we have a bunch of examples of that, so you can take a look at these details. And basically, once you have the bounds for each of these conditional expectation values, then you can use that to impute the missing counterfactual, okay? And then do the optimal policy learning. So the idea is very simple. So here's the illustration with a discrete covariate. So in this sort of hypothetical example, there is a risk score. It's on the x-axis. In the y-axis, it's probability of no new violent criminal activity. So that's the outcome you want to increase that probability. And suppose the existing policy is anything above 10 or higher is cash bail, and anything below 9 or lower is signature bond. In those cases, we identify the outcome under the cash bond, right, as you see in the blue dots on this side. However, on the other side, you have to extrapolate, right? So within some model class, you get these partial identification bonds. Same thing for the signature bond outcome. On the left of this existing threshold, you identify them, but on the right of it, you have to extrapolate. And under some model class, you have partial identification bonds, and then you figure out, okay, the new policy can be run by moving this threshold. And then you say, okay, well, this outcome is higher, so we can move all up to here. But once you go here, the next one is you're not sure. Then you fall back on existing policy. And so the simplest case is like a regression discontinuity design type of approach where you're trying to move the threshold and try to learn a policy that results in a better outcome. And we sort of on a separate paper, we're working on RD case with continuous force invariant. So, okay, so that's basically the basic idea. We call this population safe policy. So far, I'm sort of ignoring the empirical uncertainty. You can show that the value of the safe policy is at least as high as the baseline policy. So it's never do worse. But this safety obviously comes at the cost of potentially suboptimal policy. So we can compare this safe policy to Oracle policy. So Oracle policy is the best policy one could get. And you can show that the difference between the value, so we call this optimality gap between the safe policy value and Oracle, the value under the Oracle is bounded by the size of the model class. Okay. In this case, I'm writing the simplest sort of case where it's the width of the bounds. So the higher the width of the bounds, the potential gap between the Oracle and safe policy is larger. You also see the utility is multiplied by. So the higher the utility is, the consequence is higher. So the uncertainty in terms of the bounds, that basically gets multiplied, right? So the even tiny uncertainty, if the utility value is high, have a large consequence. So that leads to potentially more suboptimal policy. Okay. So there is sort of tighter the partial identification is, there's a trade-off between the identification. If you make a stronger assumption on model class, you have a tighter partial identification and a small optimality gap, but the restriction on the model class may not be realistic. Right? So there's this like trade-off between the two. Now we can also extend this to the empirical safe policy, because in practice we don't actually know for sure, right? We have to use a finite amount of data. So in this case, we basically construct a larger empirical model class, which contains the true model class with some probability. We often use like simultaneous confidence bands to get to estimate these bounds. In our applications, it's X is discrete, so we just try to get the pointwise bounds using the simultaneous confidence bands. And then we just basically impute using these bounds and do the optimal, then solve the empirical welfare maximization problem as usual. Okay, so this procedure basically has statistical properties. This gives a statistical safety guarantee with some alpha level. So compared to the existing policy, the value under the safe policy is at least as high with some probability. And the bound is basically governed by the complexity of the policy class. So the more complex the policy class is, you might need more data to avoid overfitting. So simpler policy class would give you a tighter result. And we can basically extend the same results that we had earlier for the population safe policy to the empirical case by just looking at the empirical gap, empirical model class size. In this case, just the width of the bounds, empirical bounds. And the only difference here is, again, the complexity of the policy class comes in. But in many public policy settings, policy class is relatively simple. Okay, and again, there's the same trade-off between the safety and the optimality. The more restrictive assumptions we make on the model class, tighter the identification we get, better optimality results, but the restrictions on the model class may not be realistic. Okay, so in the paper, I'm not going to talk too much about this, but there are a couple extensions. First extension is incorporating experiments, evaluating the deterministic policy. So this is a type of experiment we conducted where the control condition is like null policy. In our case, we don't give any access to, judges have no access to PSA. So if you think about it, like when you're evaluating this type of algorithmic recommendation in a very consequential setting, you cannot randomize algorithms. Okay? That's like not ethical. So the only thing you might be able to do is to withhold that information, which is what we did. But we don't randomize the algorithm itself. Okay? So, however, if this information, the control condition where there's no access to PSA, can be used by working with the treatment effects instead of outcomes. So instead of putting the restriction on the outcome model, we can put the restriction on the treatment effect model. Often we think that treatment effects may be simpler than the outcomes itself. So restriction on the treatment effects model might be more realistic. In the paper, again, we also incorporate the human decisions with algorithmic decisions. Here, like you can think of it, human decision has some cost associated with it. So if you incarcerate someone, that would incur a variety of costs. And that might be something you might want to account for. And then you have to do like worst case, analysis for both potential decision as well as potential outcomes. So if you're interested in that, it's written, it's in the paper that has the details. All right, why don't I pause here because the last part is the empirical results and see if there's any questions.
I think Eli has done a great job actually answering all of the questions. So you can feel free to continue.
Okay, great.
Maybe at the end we can take some.
Awesome, thanks, Eli. Okay, so I'll give you some empirical results from the data that of the experiment that I introduced earlier in the talk. So the first thing I want to do is show you how we can learn a new NDCA flag threshold. Okay. So we try to find improved NDCA flag threshold using the same set of risk factors. So if you recall, status quo policy is to give NDCA flag 1 if the risk factor, which ranges from 0 to 6, is either 4, 5, or 6. Okay? That's a status quo policy. And what we want to learn, the policy class, is different threshold. So maybe we should do threshold should be 5, not 4, 6, or maybe 3. We're going to use the Lipschitz constraint on this is model class restriction on the conditional average streaming effect. And then we use the simultaneous confidence interval in the linear regression framework to get that empirical model class. And we're going to set the cost of triggering the NDCA flag to be 1. You might think why there's a cost. Well, you can always trigger the flag. That's just a piece of paper, so there's no cost. But there's some fiscal cost downstream, fiscal costs on jurisdiction if it ends up into incarceration, or some socioeconomic costs on those individuals and community. We're going to assume the utility is does not depend on the action, so the cost of NVCA is always same. Okay, so the first step we're going to do is to extrapolate the conditional average stream effect. Okay, so again, the purple dot line is the existing policy, okay? And we can look at the effect of providing PSA on no NVCA probability. So what this means is that in the experiment, because it's randomized, whether to provide the PSA or not, we can identify these effects for not triggered below 4, and then you can identify that effect for trigger case above 4. Okay? So the orange one is not trigger case, and blue one is the trigger case. So these can be estimated with confidence intervals. And because for non-trigger case, the effect seems fairly constant, we place a Lipschitz constant that says that these effects shouldn't deviate too much when you go from one score below to the higher. And that's why you see these extrapolation, it's kind of hard to see, but orange bar is not huge. Whereas on the trigger case, the estimates vary quite a bit. So the same Lipschitz constraint type of assumption leads to a huge extrapolation bounds for the cases that are below 4. Right? So you can see that orange one is more informative because when we estimate it, we see that's fairly stable, whereas the blue one is, when we actually observe them, the effects vary quite a bit. So the extrapolation is going to be much more uncertain. Okay. So this means that we might be able to learn moving this threshold to the right, but maybe not too much to the left, because as soon as you try to move to the left, you're so uncertain that you can't really be confident that the new policy will improve. So the only chance is to go to the right. And that's what you exactly see. So here, I'm showing you the confidence level on the y-axis. And on the x-axis, I changed the cost of new violent criminal activity from 1 to 20 times. And this is a threshold value. And the threshold value, the existing threshold is 4. And what you can see is that in some cases, it says increase the threshold to either 6 or 7, which is actually much more lenient policy than the existing policy. And this type of method would do aggressively if the confidence level is really low. So then it's willing to change because it's willing to ignore the empirical uncertainty variation. Whereas if you want the confidence level to be high, it's a bit more conservative. So as soon as the cost becomes too high and consequence of uncertainty becomes really large, it falls back to the existing policy. So that's basically sort of what you can do, how to learn new thresholds. And you can also learn, like the second thing we did was learn a new point system. So if you remember the integer weights that they have applied to 7 binary risk scores. And so they basically add up, each factor gets weighted by some integer factor. And then if it's greater than or equal to 4, the flag gets turned on. So we're going to try to learn the policy class where we change different, look for different integer weights. So keep the structure the same, but try to improve it by looking across different integer weights. And we consider additive models as well as like second-order interaction models. Again, there's lots of choices here one could explore. And we also try like outcome versus the, putting the model restriction on the outcome versus on the conditional average stream effect. So here, like you can see, like empirical size of the model class. So the x-axis, you have confidence level, and the y-axis, I have size of the model class relative to the maximum size that one could get under this setting. And we have 4 different models. So additive outcome model, additive effect model, as well as second order outcome model and second order effect model. So this on the right column is basically modeling the effect, stream effect, conditional harvest stream effect. On the left column, you're modeling the outcome instead. So what you notice is that additive models are identifiable. You see this by looking at the confidence level of 0, which becomes the model class becomes 0, right? So it's perfectly identified. So the model class is 0. There's no partial identification here. As you increase the confidence level, you get model class get bigger, right? Because the bounds get wider and wider. And then we also see that there is a greater uncertainty for MVCA flag 1 case, as we saw in earlier, partly because there is a smaller sample size. So then you can start learning different weighting scale. So this, I picked a particular model, particular confidence level. This is the existing weights, and this is the cost of MVCA, so varying the cost of MVCA. And as you can see, like when the cost is relatively low, they're willing to change the safe policy methodology is willing to propose the weights that are different from the original weights. However, as the cost increases, it falls back to the original weights. Okay, so that's again the sort of same pattern that we observed there. And this is just how much the changes there is over the status quo policy in terms of what's the percentage of recommendations that are actually changed by changing the policy, the integer weights. And you can see that when the confidence level is low and cost is low, there's a lot more changes. And as the cost becomes higher and confidence level gets bigger, then there's very few changes from the status quo. Okay, so lastly, quickly, we can also run new DMF matrix. This aggregates FDA and CA scores into a single recommendation. We had 2 6-point ordinal scores, and we're going to use additive treatment effect models. And the policy class, we're going to try to keep the structure of monotonically increasing in both directions. So if you have higher points, you should never get more lenient recommendation. I'm going to just quickly go this. I don't want to take up all the time. So here is like what you can do is like different confidence levels on the rows and different cost. And dotted line is the existing policy. And you can see the existing policy, it converges to existing policy when the confidence level is high, as high as 20% if the cost is high enough. And so it seems like this matrix, it's DMF matrix, it's hard to learn new policy unless you can be really aggressive in terms of confidence level. All right, just to wrap up, so deterministic decisions and recommendation algorithms are ubiquitous. I think you see this around, like a lot of government welfare policies, COVID, vaccination recommendation, if you're above 65, those are deterministic recommendations, medical treatment choices. So transparency and simplicity is important for these type of usage. So that's why we see deterministic decisions. So we basically extrapolate and use both optimization to learn use policy in a safe way, with the partial identification and finding a policy that's the best in the worst case scenario. So this gives a statistical safety guarantee relative to the status quo, and that's the important part. Some evidence that we can improve PSA, but we need more data to really determine that. There are lots of, I think, other potential applications of this type of approach, and I'm looking forward to hearing from the comments from Yifan. Thanks.
Thanks, Kosuke. Sorry, Georgia, I'll let you go.
All right, I was also going to say to thank Kosuke for the excellent presentation, and thank you, Eli, for answering the comments. We will move to Yifan's discussion, and then Kosuke and Eli, you guys will have some time afterwards to respond to the comments, and if there's questions in the chat, we can take a few then.
Okay, thank you for the invitation, and it is my great pleasure to be here to discuss the inspiring work by Professor Imai and his colleagues on safe policy learning through extrapolation with application to pretrial risk assessment. So I really enjoyed the paper and talk, and many important contributions have been made in the paper, including relaxing the positivity assumption and also like incorporating this human decision making in the exciting applications. So I'm not going to like repeat all of them, but instead I will be focusing on one unique contribution made by Kosuke. Is the max-min policy is not only conservative but also safe. So throughout, I will be on the population level, rather talk about the population level rather than the empirical analogs. So there will be no statistical estimations involved here. So Kosuke's paper considered this max-min decision model. So the target policy pi-inf is their target which maximizes the minimum utility function. And this max-min decision model, the history traced all the way back to Abraham Ward in 1950s. So while this max-min decision model is not new, Kosuke brought this like new blood to this concept and gives a very nice interpretation that the max-min policy is a safe policy. So here, the safety issue is very crucial in policy making, and in particular for the forensic decision making and also the medical decision making. So caveat here is that the value function of the baseline policy, the V pi tilde, is point identified. So that as long as the baseline policy pi tilde is in the policy class capital pi, this pi inf, the safe policy will do no worse than the pi tilde on average. So to me, this is a very excellent observation and add to the max-min decision model. So the max-min decision model is getting more and more popular recently in the policy making. Here are some recent like examples. The first one is Moore et al. They considered the max-min policy in a covariate shift setting. So here everything is perfectly identified. The treatment effect is identified. So they consider there is a mismatch between the test data and the training data. So this discrepancies in terms of the distribution of the covariates. And the second one is pessimism RL. So one of our moderators, Ying, has a very nice paper on this topic. This pessimism RL is an emergent field, and there are many other works. I couldn't list all of them here. So very similar to Kosuke's framework, which relaxes the positivity assumptions. This pessimism RL relaxes this full coverage assumption of the offline data. So they do have some intrinsic similarities. And the third one is what I have worked on is for example, we have the observational data or the randomized trial subject to the non-compliance, then the no unmeasured compounding assumption might not necessarily hold. So how to make decision under such uncertainty, and in particular, how do we make the decision when we have this instrumental variable bound? So the max-min model is one particular strategy. So next, what I'm going to do is to borrow Kosuke's equation 5 to duplicate my setting a little bit more. And then I will map it back to the Kosuke's problem and ask one question. So my setting is super simple, subject to some potential unmeasured compounding. So we consider the Mansky types of bound. So for example, Robbins-Mansky bond or Belky-Pro bond. So the setting is essentially as the figure shows. So the conditional counterfactual means are bounded below and above. And let's revisit Kosuke's equation 5. The really cool thing in his setting is this left-hand side and the right-hand side are the same. Unfortunately, this is not the case under my setting. Let me redefine the M as the counterfactual means instead of the conditional means. Recall that in Kosuke's setting, the M was defined as a conditional means. So here I redefine as counterfactual means. So while the expressions on both sides are literally the same as the equation 5, the equality does not hold. And the left-hand side actually corresponds to a pessimism decision-making, and the right-hand side corresponds to a standard of care decision-making. And in most cases, they are not the same. And furthermore, on the right-hand side, one can replace this pi tilde with the optimal pi star. So it becomes the minimax regret approach, which was originally proposed by Leonard Savage. And there are also work explored this direction with the deterministic policy. And here, in fact, considering a stochastic policy will give a smaller maximum regret. So in this setting, there are many possible decision-making strategies. So now let's map it back to Kosuke's problem. And I'm curious, what would be a minimax regret policy be here? So I'm not saying that practitioners should use the minimax regret policy because the minimax regret policy would not be safe. So I'm just curious about, like, would the minimax regret policy add any additional insight to the safe policy pi-inf? Or do you have a sense how it would be different from the safe policy pi-inf? And my second question is on the individualized safety, which you also brought it up in the end of your paper. So I'm curious, would it be a straightforward extension based on your nice framework, or it would requires some more effort? Would like to hear your or Eli's thoughts on it. Thank you, really great work.
Thank you, Yifan. Kosuke, do you want to respond?
Yeah, thanks for your comments. Okay. Yeah, I guess I've thought a little bit about the individualized safe policy. I guess there you can, I guess it depends on what we mean by that. But if you mean by like making sure that, you know, every individual, well, I guess it could be related to some kind of like quantile treatment effects in the real sense, in terms of like looking at the effect sizes across all individuals, and then making sure that certain percentage of people are, you know, not harmed by this new policy relative to the existing policy. So I think that's something that we thought about. Well, we haven't really done anything, but we talked about, you know, possible extension, because it's, you know, the individual level treatment effects is obviously unidentifiable. So we can think about the quantile of treatment effects instead of the usual quantile of treatment effects, which I think it's quite different. And most policymakers would be interested in the one you just mentioned. So I think that's a really nice extension, especially with some of this, you know, work on the statistical uncertainty of the individual treatment effect estimation. We might be able to incorporate some of that into empirical model class type of estimation. The point that you were talking about, so you're talking about, like, when you say counterfactual mean, you mean that without like any conditioning of like X or any of that. Like I'm trying to understand the difference in your setting, between your setting and ours.
I guess the difference is basically the definition of the M. So the M in your setting is, the notation is literally the same, I guess, the MAX, and the MAX is defined as the conditional means in yours. And in mine, it's just the expectation of the potential outcome given the X. So yeah, that would mean I meant by the counterfactual means.
I see. Maybe Ira has something to add there.
Yeah, I think I think your point that in our setting we can identify the value of that baseline of status quo policy, I think is you're right. That is exactly the key point that we can get this property. So I think that when we don't have that, so like in your setting with this unmeasured confounding where you can't say that you have something like that, I think you're absolutely right to point out that a lot of these other kinds of questions about, well, what are you comparing regret to, start to become really, really important. So in our case, we have this sort of natural choice, which is the baseline. But for instance, if we wanted to think about sort of the regret relative to the oracle, right? Then that would lead us back into this sort of more tangled world and more kind of difficult world of trying to figure out these regret things, because that's something that we can't identify, right? So then we come back to those problems.
Yep, that makes sense. Yep.
All right, thank you, everyone. If somebody from the audience still has questions, feel free to ask. Let's wrap up the seminar for today. Just 1 second. So next week, we'll have Yuan-C Chen from Duke University, who will be talking to us about domain adaptation under structural causal models. We hope to see you all there.